and today we are going to discuss the thermodynamic processes. We have discussed what are the thermodynamic properties, and we will also be discussing how they are related to each other. And I told you that the thermodynamic properties are point functions, whereas heat and work, they are the path functions. A point function means that the change in that property, or also known as state variable, depends upon the difference of the endpoints only. So suppose we have the system moving from 1 to 2 following this path and following another path, two paths, there are more than two paths, A, B, C. X is the property or the variable, so x2 minus x1 following the path A is equal to x2 minus x1 following the path B, x2 minus x1 following the path C. That means change in the variable x, that is dependent upon the difference of the final minus initial state endpoints. So it is called a point function. If it is dependent on the path followed, in that case it is called the path function. So here the system properties which we discussed last time, they are point functions. Internal energy, pressure, volume, entropy, Helmholtz function, Gibbs function, etc. They are the and temperature point functions, and they do not depend upon the path followed. Whereas heat and work, W, they are dependent on the path followed, path functions. So heat or work exchange during these three different paths will be different. So that's why they are called the path functions. Now we have to discuss thermodynamic processes. So we know what is a system. System we have discussed in the previous discussion. After this, how is the system defined? And this is similar to the situation that you are at a certain place and someone calls you from home. Where are you? So you will define your position with the help of certain coordinates. And what are those coordinates? I am at this much distance from home in this direction. So you have explained your position in terms of distance and the direction. Direction means the angle. So you have certain variables with respect to which you can define your position. Similarly, the system can be defined with certain parameters at any moment, and position of the system can be defined, and these parameters are called state variables or the properties of the system, which I have written here. So let us take an example. We have this piston and cylinder arrangement. It is moving in this, contains a gas. Let us assume that this is an ideal gas. You give it energy, heat it, the ideal gas, and suppose initially pressure and volume inside this, they are specified. This is the pressure P1, pressure axis, volume axis, and this is V1. So initially the system is existing in this state. So we define the state. This is a state where the system is existing. How is the system existing? When the parameters which define the position of the system at that time, they are completely defined, then system is said to exist in a state. This is how you define the state of the system. And state variables or these parameters, they are called the thermodynamic properties. So we can write that system exists in a state when the state parameters or the system properties are completely defined. So here pressure, volume are defined and the system is in equilibrium. And now you start heating this system. Then what will happen? This piston will move further to different positions as the energy of the gas is increasing. As a result, the molecules of gas, they are applying more and more pressure on this walls of the cylinder as well as on the piston. So now if the system is moving like this, then the pressure is changing. First the pressure is increasing, then this system will move. The pressure inside this is increasing first. As a result, it will push the piston in this direction so that the pressure is reduced. Suppose this is the new pressure P2 and the volume changes here V2. So if we have this type of equilibrium points, if we attain more and more equilibrium points like this, and they are very close to each other, and you join all these equilibrium points, then we attain a process. So we can say that a thermodynamic process is the continuation of the equilibrium points, thermodynamic equilibrium. Here I must use the word thermal equilibrium. So thermodynamic equilibrium, not thermal equilibrium. Thermodynamic equilibrium means equilibrium. You all know what is equilibrium. Means net force acting on a body in any direction is zero, net moment is zero. Here we are talking about net force only. So thermodynamic equilibrium comprises of thermal equilibrium and mechanical equilibrium and chemical equilibrium. This is the thermodynamic equilibrium. Thermal equilibrium means the temperature has become constant, so there is no flow of heat energy inside a body. This is a body, and suppose heat is conducted in this direction. Temperature of this end is T1, this end is T2. Heat is flowing like this. So in equilibrium, when there is no temperature difference inside a body, then there is no heat flow or no heat exchange between two bodies. Thermal equilibrium. Chemical equilibrium means there is no concentration difference inside the system, and so there is no flow of the fluid from high to low concentration. And mechanical equilibrium means there are no unbalanced forces which are acting on the system. So when these three equilibriums are established, then we say that the thermodynamic equilibrium has been achieved. So if this process is occurring in such a way that we get a continuation of these states, these are equilibrium states, and when we join these, then we get the thermodynamic process. So this is the basic of a thermodynamic process. Now let us discuss what are the various types of the thermodynamic processes. And here I am talking about the ideal things, that is the ideal system. There is no loss of energy in friction. Actually there are losses of energy. Let us talk about the thermodynamic processes. What are different types of thermodynamic processes? The isothermal process, adiabatic, isochoric, isobaric. The general polytropic process can be written by P V raised to the power n is constant. V here is specific volume, that is volume divided by mass, specific property, which is not dependent upon the mass. So these are different processes, and this can be defined by the value of n. Isothermal means temperature remains constant during the process. The general equation is PV equal to constant. Adiabatic means net heat exchange of the system with the surroundings is zero. No heat given, no heat taken. This is adiabatic process. The equation is PV raised to the power gamma, here is constant. Gamma is the ratio of specific heats of a gas at constant pressure and constant volume. Isochoric process means there is constant volume for the system, and the equation is volume equal to constant. Isobaric means pressure equal to constant. This is the equation. So we can show these processes on a diagram, and we can write the value of n for different processes. If n equal to 0, this means P V raised to the power 0 is constant, isobaric process. If n equal to infinity, that means P V raised to the power infinity equal to constant, or I can write it like this. So this gives V equal to a new constant C1, isochoric process. If n is equal to 1, PV equal to constant, that is temperature is constant. Isothermal, n is gamma, this is adiabatic. We can show these processes on property diagrams. This is isochoric, this is isobaric, isochoric, and we have this process isothermal and adiabatic. PV raised to the power gamma equal to constant. So n here is 0, n is 1, n equal to gamma for this one, and n equal to infinity for this. So you can see that n is increasing in this direction. So these are the different thermodynamic processes. So in the next discussion we will discuss about the specific heat and what is the work done by the system during a thermodynamic process.